You are out past Pluto now. The sunlight is weak, the radio delay is long, and a machine no bigger than a small car is drifting through a darkness so wide it almost stops feeling real. The subject is the Heliopause, a thin, mostly invisible border at the far edge of the sun's great bubble, older in idea than in proof, quieter than any planet, and easy to ignore until it suddenly refuses to be ignored. What happens there helps decide how much of the raw galaxy leaks into our neighborhood, and the more scientists measure that border, the less it looks like a soft, fading edge, and the more it looks like a real wall of heat and pressure. Settle in and follow this story with me, and you will start hearing the outer solar system not as empty silence, but as a living frontier that keeps changing under our feet. At first, nothing about that frontier seems dramatic. No flames, no cliff, no giant gate hanging in space, just charged particles, magnetic fields, and a very old spacecraft sending home tiny changes in numbers. But numbers can be louder than pictures when they come from a place no human being can ever stand. The farther Voyager flew, the more those numbers stopped acting like a calm ending and started acting like weather at a coastline. And that is the strange part. We are talking about the farthest edge of the sun's reach, a place most people imagine as colder, emptier, and less eventful than anywhere else. Instead, scientists found tension there, compression there, and temperatures that sounded almost absurd for a place so far from any fire. Before this becomes about the science, it begins with something simpler. Most people believe the outer edge of the solar system must be the coldest, emptiest, calmest part of our neighborhood. The farther from the sun you go, the more the heat should fade, the particles should thin, and the whole system should quietly dissolve into the black between the stars. That idea feels natural because our daily lives teach us that distance means less heat. Stand close to a stove and you feel it. Step back and the warmth drops away. If the sun is the source of energy in the solar system, then the places farthest from it should feel like the deep freeze at the back of a garage in winter. The planets seem to support that picture. Mercury gets scorched. Earth is warm enough for oceans. The giant planets sit in dimmer light. Beyond Neptune, sunlight is so weak that noon there would feel like a rumor. It is easy to think the whole story of the outer solar system is one long slide into cold. So for years, the common picture was simple. The sun's influence spreads outward. It gets weaker and weaker. Then, at some huge distance, it just gives way. No sharp drama, no sudden pressure line, just a smooth handoff from our star's neighborhood to the wider galaxy. That picture leaves out one huge fact. The sun does not only shine, it also blows. Every second, it throws out a stream of charged particles called the solar wind. Charged just means the particles carry electric charge. That matters because charged particles listen to magnetic fields. Over time, that wind builds a giant bubble around the sun and planets. Scientists call it the heliosphere. It is not a shell you could see through a telescope. It is a moving region made from hot, thin plasma. Plasma is gas whose atoms have been stripped apart into charged pieces. Inside that bubble, the sun still sets many of the rules. Its magnetic field helps guide particles, its wind pushes outward. Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and every smaller body orbit inside this giant shifting shield, whether we think about it or not. That shield matters more than most people realize. NASA's Jet Propulsion Laboratory has said Voyager 1 showed that the heliosphere protects Earth and the other planets from more than 70% of incoming cosmic radiation from outside the solar system. So this is not just a story about faraway space. It is also a story about the roof over our heads. For a long time, scientists expected that roof to have an outer edge called the heliopause. The heliopause is where the solar wind can no longer push the galaxy aside. Inside, the sun's outflow dominates. Outside, the local interstellar medium, the thin gas and magnetic field between the stars, pushes back. Even that sounds cleaner than reality. We love borders that behave like lines on a map. We want inside and outside. We want before and after. We want one number to drop and another to rise, and then we want the story to be done. But space is rarely that polite. The sun moves through the Milky Way. The interstellar medium is not empty. Magnetic fields bend. Plasma compresses. Pressure builds. The solar cycle rises and falls over about 11 years. So the heliosphere can expand and shrink like a giant lung breathing in slow motion. That meant the boundary might move. Yet movement is not the same as violence. A person can still imagine a soft edge that simply shifts in and out. And for decades, that remained the broad public picture. If drama lived anywhere, it lived near the sun, in solar flares and bright storms, not in the dim wilderness beyond Pluto. Then there were the Voyagers. Voyager 2 launched first on August 20th, 1977. Voyager 1 launched on September 5th, 1977, on a faster track. NASA built them to study Jupiter and Saturn. Later, Voyager 2 went on to Uranus and Neptune. Then both spacecraft kept going, long after the famous planet photos were done. Voyager 1 reached Jupiter on March 5, 1979, and Saturn on November 12, 1980. Voyager 2 reached Jupiter on July 9, 1979, Saturn on August 25, 1979, Saturn on August 25, 1981, Uranus on January 24, 1986, and Neptune on August 25, 1989. After that grand tour, the mission changed shape. The target was no longer a planet, it was the edge itself. NASA called that extended journey the Voyager interstellar mission. The goal was simple to say and hard to survive. Keep the spacecraft alive long enough to cross the sun's boundary and tell us what the frontier is actually like. That meant decades of power management, careful engineering, and patience almost beyond belief. Think about the human side for a second. These spacecraft were launched when Jimmy Carter was president. They were built before smartphones, before the internet became everyday life, before many adults watching this video were born. And yet they kept flying, carrying a few working instruments into a place no machine had ever sampled before. Long before the final crossing, the Voyagers had already begun to hint that the edge would be strange. In the early 1990s, JPL reported evidence of low-frequency radio emissions that likely came from solar material interacting with colder interstellar gas beyond the Heliopause. Don Gurnett at the University of Iowa was one of the scientists tied to those measurements. That clue still fit the old story well enough. A border existed. Fine. But a border is not yet a wall. A shore is not yet a storm. Many scientists still expected the heliopause to behave like a boundary you could describe with one neat sentence and one clean diagram in a textbook. Ralph McNutt of the Johns Hopkins Applied Physics Laboratory helped estimate where that boundary might lie, on the order of around 90 to 120 astronomical units. One astronomical unit, or AU, is the distance from Earth to the Sun. Already we were talking about a border so far away that Earth's orbit became the measuring stick. Then Voyager 1 reached the termination shock on December 16, 2004, according to NASA. That is the place where the solar wind slows sharply before the outer boundary. Expected result? A gradual approach to the end. Actual result? A layered structure with stages. It was less like leaving one town and more like driving through outer roads, then suburbs, then a messy industrial edge. After that, Voyager 1 entered the heliosheath, the outer layer of the sun's bubble. If you want a home-size comparison, picture the space between your front door and the street during a storm. The warm house is not the whole story. The porch matters too. That outer strip is where wind, cold, and shelter all meet. By then, the main assumption was still alive. Space gets colder and calmer the farther out you go. The edge may wiggle, but it should still feel like a fading line. If you had to choose one place for almost nothing to happen, you would have pointed to the deep outer dark. That was the setup. A simple map, a clean ending, a quiet frontier. The farther edge of the solar system looked like the most likely place for the story to become less interesting. But that picture was about to break. The numbers coming from Voyager did not describe a soft fade. They described a stressed boundary where particles dropped away, galactic particles rushed in, and the medium around the spacecraft behaved as if it had been squeezed. Mark the moment your old map fails in your mind and hold on to it, because noticing that crack is how you learn to spot real discovery. Moments like that also help this channel chase the next story that looks simple until the data says otherwise. What changed was not one headline. It was a sequence of signals that refused to fit the clean old picture. Something was waiting at the edge of the solar system, and it was bigger than a single crossing event. In 2011, Voyager 1 began to see energetic particles from inside the heliosphere decline. Scientists expected those particles to weaken as the spacecraft moved outward. What they actually saw was a much sharper fall. It felt less like turning down a radio and more like the station suddenly vanishing while you were still holding the dial. At the same time, galactic cosmic rays increased. Again, a rise was expected eventually, but the jump looked dramatic. The old picture said inside particles should fade slowly while outside particles slowly mix in. The new picture looked like stepping through a doorway and hearing one room go silent while another room starts roaring. That pointed toward the heliopause, but another clue seemed missing. Scientists had expected the magnetic field direction to change more clearly when Voyager crossed into interstellar space. Instead, the field beyond the boundary looked strangely aligned with the field inside. That left the team in a strange place. The signs said crossing. The field said maybe not yet. Gurnett said the team literally jumped out of their seats when they saw the oscillations. The reason was simple. Dense plasma of that kind was what they expected in interstellar space, not in the solar bubble. The evidence forced a rethink of when Voyager had actually crossed the Heliopause. The team went back through earlier data and found fainter oscillations in October and November of 2012. Using those events, they concluded that Voyager 1 had first entered interstellar space in August 2012. NASA fixed the crossing date at August 25, 2012. The craft had crossed the boundary earlier than the full proof arrived. That alone would have been historic enough. Voyager 1 became the first human-made object to enter interstellar space. Johns Hopkins APL described it as a historic leap. Stamatios Kremigas, principal investigator for Voyager's low-energy charged particle instrument, used a striking comparison. He said the crossing was like leaving the hot, million-degree atmosphere of the Sun and entering the cold, 5,000-degree atmosphere of the galaxy. That comparison sounds like the old map winning after all. Hot inside, cooler outside. Case closed. But the surprise was not about one simple inside-outside temperature switch. The surprise was about what the boundary region itself was doing and how much structure it contained. Remember the expectation. At the edge, things should just thin out. Outside should be colder and denser, yes, but the crossing itself should still be simple. What scientists found instead was a perturbed region, a disturbed transition, not a neat line. Some effects from the Sun were still present even after the crossing. Kremigas also said Voyager was not yet in pristine interstellar space. That word pristine matters. It means untouched, undisturbed, fully separate. Voyager had crossed the boundary, yes, but it had entered a transitional region where the Sun still left fingerprints. So the border was real, yet the change was not clean. That alone made the frontier feel more like surf than like a painted line. Voyager 2 gave the story its second chance to prove itself. One spacecraft can trick you. Two spacecraft, crossing at different times and places, let you test whether the first event was a fluke or part of a larger pattern. Voyager 2 reached the Heliopause on November 5, 2018, at about 11 billion miles or 18 billion kilometers from Earth, according to JPL. In 2019, 5 papers in Nature Astronomy described what Voyager 2 saw. JPL summarized the results in clear terms. Inside the heliosphere, plasma is hot and sparse. Outside, it is colder and denser. That matched part of the old expectation, but only part. Scientists expected the plasma just outside the heliosphere to be colder than the plasma inside. Voyager 2 confirmed that. But it also found the plasma outside was slightly warmer than expected. JPL said this could mean the plasma was being compressed. Expected result? A cooler outside region. Actual result? A cooler outside region that was still unexpectedly warm. It was like stepping into winter air and realizing the wind had been squeezed through a narrow alley. Voyager 2 found another clue just before the crossing. The plasma density increased slightly on the inside edge of the heliosphere. Again, that hinted at compression around the bubble itself. So the boundary was not just a handoff between two environments. It looked like a zone where both sides were being pressed. That is one of the roots of the so-called hot wall. Not a wall of stone, not a wall of flame. A wall in the sense of a thin, stressed boundary layer where plasma piles up, compresses, and heats. This is why the story sounds impossible if you picture heat only as something you feel from a campfire. In space physics, temperature can be very high even when the gas is so thin it would not burn you the way fire does on Earth. Temperature, in this case, reflects particle energy, not cozy warmth. A few very energetic particles in a very empty region can add up to a huge temperature number and still leave the space itself almost unbelievably thin. D.A. Gurnett and colleagues published another 2019 Nature Astronomy paper on plasma densities near and beyond the heliopause from Voyager 1 and Voyager 2. Their work strengthened the view that the region around the boundary was structured and changing, not simple and still. The solar system's edge was behaving more like a coastline with currents, pressure, and layered water than like the clean edge of a glass bowl. JPL added one more critical point. Voyager 2, like Voyager 1, was not yet in undisturbed interstellar space. It appeared to be in a perturbed transitional region just beyond the heliosphere. That means the Sun's influence still reached into the space outside its main bubble. The old idea of a crisp finish line had to go. Ed Stone of Caltech put the broader meaning in plain language. He said the Voyager probes are showing us how our sun interacts with the stuff that fills most of the space between stars in the Milky Way galaxy. That is a beautiful sentence because it flips the whole story. The edge is not where the sun stops mattering. It is where the sun's argument with the galaxy becomes visible. Voyager 2 also hinted that the heliosphere is not perfectly sealed. One of its particle instruments showed that a trickle of particles from inside the heliosphere was slipping through the boundary and into interstellar space. JPL compared the heliosphere to a ship whose hull is somewhat leaky. Expected, a tight barrier. Found, a porous shield. It was like finding cold air sneaking around a window frame you thought was closed. That leakiness may depend on location. Voyager 1 crossed nearer the front of the heliosphere relative to the bubble's motion through space. Voyager 2 crossed closer to a flank, and JPL said that region appears more porous. So the shield around the solar system is not only dynamic, it may also differ from one side to another. Then there was the magnetic field mystery. Scientists had expected the magnetic field just beyond the heliopause to change direction much more clearly. Voyager 1 had found the field outside was nearly parallel to the field inside. That seemed so surprising that some researchers wondered whether it was a local coincidence. Voyager 2 confirmed the same general alignment. Expected, a sharper turn. Found, alignment across the boundary. It was like reaching a border between two weather systems and realizing the clouds on both sides are still flowing the same way. Why would that happen? Part of the answer seems to involve the larger magnetic field of interstellar space draping around the heliosphere. The shape of the bubble matters. The direction from which the solar system moves through the galaxy matters. The local interstellar magnetic field matters. Suddenly, the heliopause is not a line. It is a global structure with geometry. That is where IBEX enters the story. NASA's Interstellar Boundary Explorer, launched in 2008, watched the edge of the heliosphere from much closer to home by detecting energetic neutral atoms. Neutral means these particles have no electric charge, so magnetic fields do not bend them the same way. That lets them travel long distances and carry information from the boundary back inward. Soon after launch, IBEX saw something nobody had predicted so clearly, a bright ribbon of incoming particles across the sky. That ribbon was a clue that the interstellar magnetic field and the heliosphere's shape were tied together in ways scientists had not fully grasped. A mysterious pattern appeared where the clean old map said there should be little more than a smooth edge. In 2016, NASA described work led by Eric Zernstein of the Southwest Research Institute and published in the astrophysical journal Letters. The study used IBEX data and simulations to pin down the strength and direction of the magnetic field outside the heliosphere. That helped explain how the boundary is shaped and how particles can be reflected, recharged, and sent back inward. Zernstein described one leading idea behind the ribbon. Solar wind particles travel outward, become neutral atoms, cross the heliopause, then later lose and regain electrons in just the right way and get sent back. The whole process can take 3 to 6 years. Expected, the boundary just sits there. Found, particles are making long return trips and carrying delayed messages from the edge. It is like mailing yourself a postcard from a storm front and having it arrive years later. By now, the phrase hottest wall in the solar system starts to sound less like clickbait and more like a rough nickname for a real physical effect. The boundary around the sun's bubble contains compressed plasma, disturbed fields, and unexpectedly hot regions by the standards scientists expected for local interstellar space near the heliopause. Still, honest science includes hesitation. JPL has said scientists do not yet fully understand what causes the compression on both sides of the boundary. That matters. It keeps the story real. If every piece fit too neatly, you should be suspicious. Instead, what we have is stronger than a simple answer and weaker than a final answer. We have a frontier that has become real enough to map and strange enough to keep arguing about. So let us say clearly what changed. The edge of the solar system is not just farther, darker space. It is a stressed contact zone. It has structure. It has pressure. It leaks in places. It lines up magnetically in surprising ways. And near that boundary, the plasma can be much hotter than many models predicted. If you want the kitchen table version, imagine your house on a windy winter night. The living room is one environment. The outdoors is another. But the most interesting physics happens at the door, the window seams, the walls, the draft under the frame. That thin boundary is where pressure, temperature, and flow reveal how well your shelter works. The heliopause is that, scaled up beyond imagination. And here is where this stops being about one old spacecraft and starts being about all of us. If our solar system lives inside a moving shield, and that shield has a hot, compressed, partly leaky outer skin, then home is not just a planet. Home is a planet inside a bubble whose frontier is constantly negotiating with the galaxy. Once you see the heliosphere that way, the implications multiply fast. The boundary is part of Earth's safety system. JPL said Voyager 1 showed the heliosphere blocks more than 70% of cosmic radiation from beyond. That does not make life on Earth easy by itself, but it tells us our planet has been living under a bigger shield than most people ever picture. Cosmic rays matter because they are fast, energetic particles from violent events like exploding stars. They can damage electronics. They matter for astronauts. They matter for spacecraft traveling far from Earth. And they matter for the long story of habitability, meaning the conditions that let life keep going. So the question now is not only where the heliopause is, the question is how it breathes, changes, leaks, and responds to the sun's cycle. That is why new missions are so important. NASA's Interstellar Mapping and Acceleration Probe, or IMAP, exists to map the boundaries of the heliosphere in far greater detail. NASA says IMAP launched on September 24, 2025, at 7:30 a.m. Eastern Daylight Time from Kennedy Space Center's Launch Complex 39A aboard a Falcon 9. It operates from the Sun-Earth L1 point, about 1 million miles from Earth toward the Sun. From there, it can collect particles from the Sun, from the heliosphere's boundary 6 to 9 billion miles away, and from interstellar space. Think about how different that is from Voyager. Voyager is a needle moving through one path. IMAP is more like a weather satellite for the invisible frontier. Instead of waiting decades for one spacecraft to reach one crossing point, scientists can use tiny neutral particles to build a wider map of the whole bubble. NASA says that boundary helps protect the solar system from harsher radiation from the rest of the galaxy and is key to creating and maintaining a habitable solar system. That is a big statement. It means the heliopause is not just a science fiction border. It is part of the reason the solar system is a good place for life to exist. The price of keeping that story alive is growing. On April 17, 2026, NASA said engineers at JPL shut down another instrument on Voyager 1 to save power. 2 science instruments remained operating after that step. Expected ending? Old spacecraft quietly dies. Actual ending? Old spacecraft keeps being carefully trimmed so it can continue whispering from interstellar space. It is like keeping a lighthouse lit by turning off every bulb except the ones that still matter most. The dates now begin to stack up like mile markers in a long story. August 25, 2012, Voyager 1 crosses into interstellar space. November 5, 2018, Voyager 2 follows. 2019, Nature Astronomy papers sharpen the picture of the heliopause and its disturbed surroundings. September 24, 2025, IMAP launches to map the boundary more fully. April 17, 2026, Voyager 1 sacrifices another instrument so the mission can continue. And the numbers get sharper too. Around 121.6 astronomical units for Voyager 1's crossing, based on the APL account. About 11 billion miles from Earth for Voyager 2 at its crossing, according to JPL. A plasma temperature range of roughly 30,000 to 50,000 Kelvin near the boundary in the Richardson result. These are not vague myths anymore. They are measured pieces of a frontier map. What remains unknown may be just as important as what is known. Scientists still want to understand exactly why plasma is compressed on both sides of the heliopause, how the interstellar magnetic field drapes around the heliosphere, how porous different regions of the boundary are, and how the solar cycle changes the size and shape of the sun's protective bubble over time. That means the next big discovery may not look like the last one. It may come from a better global map rather than from a single crossing. It may come from IMAP connecting the ribbon seen by IBEX to the in-place measurements from Voyager. It may come from understanding how particle pressure, magnetic direction, and plasma density fit together into one living picture. The next horizon is already in view. IMAP will keep turning tiny particles into maps of a boundary we still cannot see directly. Voyager will keep pushing outward for as long as a little power remains, and every new measurement will help answer a question that once sounded almost silly. What does the edge of the solar system really feel like? Save this story somewhere quiet. Screenshot the date, remember the mission names, or simply come back the next time you hear heliosphere in the news. Keeping these details close will make the next update feel less like random information and more like the next page of a book you are already inside. So leave with one image. A small machine launched in 1977 drifts beyond the planets. A pulse from the sun reaches it after more than a year. The plasma around it trembles. Back on Earth, scientists see the signal and realize the border around our star is not a gentle fade into nothing. It is a compressed, hot, shifting frontier. A real wall, if by wall you mean a place where one world pushes against another and the pressure becomes impossible to ignore. Not the hottest place in the solar system in the everyday sense, but one of the strangest hot boundaries we have ever found. And the quiet conviction at the end of all this is simple. Tomorrow, or next year, or a few years after that, someone will sharpen this picture again. The map of home will grow, the edge will become clearer, and we will keep learning that the future of discovery often waits in the places we once called empty.